simple harmonic motion. If a particle is moving in simple harmonic motion, all it means is that it's moving between 2 points back and forth. And a nice example of this is a pendulum going from one point to the other, back to the starting point, and in between the 2 points. And if something is moving in simple harmonic motion, it's most likely going to be represented with a sine or cos function, because we know that a sine and cos function oscillates between 1 and -1, or 2 and -2, depending what the amplitude of the function is. So let's have a look at an example, looking at if x was to equal 4 cos 2t. And let's sketch this out. And we know this is going to start up at 4 and come down to -4 and back up to 4. And we know its period is going to be represented as 2 pi on whatever the coefficient of our variable is inside our cos function, which is 2 in this case. So our period's going to be pi. So this is going up to pi, which means this is pi on 2, this is pi on 4, and this is 3 pi on 4. So if this was our displacement function, let's imagine a pendulum scenario. So here we have our displacement being +4, and what we can imagine here is our pendulum all the way to the right. And if we imagine this middle axis, the arc that it would make here would be of length 4. So we're the distance of 4 to the right of our neutral axis there. When we're at this point here, this is when our displacement is 0. So the pendulum would be on the neutral axis there at 0. When we're at this point here, we have a displacement of -4. So our pendulum would be all the way to the left. At this point here, we're back to 0 for our displacement. So the pendulum is back over here. And then this point over here, our displacement's 4, so we're back to the right. And you can see this curve is describing the pendulum starting off on the right, swinging down into the middle, then the left, back to the middle, and then to the right. And this process repeats. You can see it's back to its starting point over here, because this is one period, and it's just going to repeat over and over again. Let's go ahead and derive our function to get our velocity. So deriving our displacement function, derivative of cos is minus sine. We're going to get minus, and we times by the derivative of the inside of our cos, which is just 2. So we're going to get -8 times sine of 2t. Let's go ahead and sketch this. So now we have a sine function, a negative sine function, with amplitude of 8. And this is going to look something like this, where we're going from -8 to 8, has the same period, so pi, and this is pi on 2, this point is pi on 4, this point is 3 pi on 4. And what's happening to the velocity? Well, here the velocity starts off at 0, which makes sense because we're still, and then as the pendulum swings down, the velocity is negative because it's moving to the left, up until it gets to this point here, where the velocity is 0, because it stops at the other extreme end and has to turn back. The velocity is now positive, because we're now swinging to the right, and here the velocity stops again at the end. Let's go ahead and look at our acceleration function now. So acceleration, derivative of minus sign is minus cos. We again need to multiply by the derivative of the inside, so we're going to get minus 16 cos 2t. And let's go ahead and sketch this out. So we have a negative cos function here. So this one's going to look something like this. This is going from minus 16 to 16 for our acceleration. Now, as this pendulum moves, it's speeding up. So when our velocity is negative and our acceleration is negative, this is represented by speeding up. So if the signs of velocity and acceleration match up, it means the particle is speeding up, but if they're opposite, they're slowing down. The acceleration here is 0 because it reaches maximum velocity, so it's no longer accelerating. And now velocity is negative and acceleration is positive, which means the pendulum is slowing up as it goes past this point to come to a stop. Acceleration is maximum when the velocity is 0. And then as it comes back down, it has positive velocity and positive acceleration, which means it's speeding up on the way down. When it gets to the middle, velocity is a maximum, which means acceleration 0. And on the way back, and then as it comes past the middle, velocity is still positive because we're moving to the right, but acceleration is now negative, which means it's slowing back up to get to this point here. So all of this motion describes simple harmonic motion, this back and forth motion between 2 points. And let's just have a bit of a closer look at the relationship between the displacement and the acceleration, because they look pretty similar. This displacement is 4 cos 2t, and the acceleration is minus 16 cos 2t. We could rewrite the acceleration as minus 4 times cos 2t, and 4 cos 2t is just x. So acceleration equals minus 4 times x. So directly related to the displacement. And this is in fact the case for all simple harmonic motion. It has to satisfy, so if we have some acceleration, so if we have some displacement in terms of t, it's only going to move in simple harmonic motion if the acceleration equals minus n squared of that displacement. And n, in this case, is going to affect the period. So this is where the period equals 2 pi on n. And in this case, you can see if we have this, we can rewrite this as minus 2 squared x. So in this case, n is equal to 2. And that's the exact value we used over here to work out our period. Let's have a look at another example with a bit more algebra involved. So we have the motion of a particle moving in simple harmonic motion along a straight line is given by the equation d2x dt squared equals minus 16x. And we want to initially, so when t is equal to 0, particles at the origin with a velocity of 4 meters per second. And we want to find its displacement at any time, which means we want to find its displacement as a function of time. and we want to state the period and the amplitude. Okay, and we know the particle is moving in simple harmonic motion. So since we know the particle's moving in simple harmonic motion, we know that it's going to satisfy a displacement equation where displacement is going to equal to some period times cos of some factor affecting the period times t plus a possible shift in the graph. And we can write this all the time when we're doing a question in simple harmonic motion. We know if it's in simple harmonic motion, we could write our displacement function as this. And we know some things already that we can put into this formula. We know that when t is equal to 0, x is equal to 0. So let's go ahead and sub those in. We're going to get 0 equals a cos of n times 0 plus alpha. So we're just going to get 0 equals a cos of alpha. We can divide both sides by a. So we're going to get cos alpha equals 0. And solving for alpha, we know that alpha must equal pi on 2. So we already got our value for alpha. So we can put that back in to our displacement. So we know x is equal to a cos of nt plus pi on 2. We also were given that acceleration equals minus 16x. And this is going to help us find our value of n. So we've got, do it over here. So we've got acceleration equals minus 16x. We can rewrite that as minus 4 squared x. And we know if it satisfies simple harmonic motion, a must satisfy minus n squared x. So therefore, n must equal 4. So we can sub that in as well. We've got x equals a cos 4t plus pi on 2. So the only thing we need to find now is the amplitude. And we were given information about the velocity. So it might help us to derive this and get an expression for the velocity. So deriving x, we're going to get v. And deriving a cos function, we're going to get negative sine. So we're going to get minus a sine of 4t plus pi on 2. And we just need to multiply by what's inside the bracket, which is 4. So we get v equals minus 4a times sine of 4t plus pi on 2. And we know from our initial conditions that when t is equal to 0, v is equal to 4. So we get 4 equals minus 4 a sine of 4 times 0 plus pi on 2. So we can divide by the negative 4. So we get minus 1 equals a times sine of 4 times 0 is 0 plus pi on 2 is pi on 2. Then sine of pi on 2 is going to give us 1. So we get minus 1 equals a, and we found our value for a. So we've got to be careful not to confuse that with acceleration. This is the a that was up here for our amplitude. This a over here was our a for acceleration. So let's go ahead and sub that back in. So now we know the displacement equals minus 1 times cos of 4t plus pi on 2. And we don't usually like writing a negative in front of our trig function, so we can actually tidy this up using our supplementary angle results. So x also equals the positive cos of pi minus our angle of 4t plus pi on 2. And let's expand that bracket on the inside. So we're going to get pi minus pi on 2, which is pi on 2, and then minus 4t. And we can just tie this up a little bit better because cos of pi on 2 minus an angle is just sine of that angle. And we get our final expression for our displacement being x equals sine of 4t. And here we can easily state the period and the amplitude. So the amplitude's nice and easy. It's just what's in front of the sine function, which is just 1. And the period we work out by doing 2 pi over the coefficient of what's inside our sine function, which is 4, and that gives us pi on 2 for our period.